Bismillahirrahmanirrahim and Assalamu alaikum. I welcome you to the lecture number 14 of electric circuit analysis. Today we are going to study capacitors and its applications. How does a capacitor act in a DC, and if we have to find the energy stored in a certain capacitor, what is the methodology followed to find the energy stored in a capacitor. First of all, we will concentrate on example number 6.3. In this example, we have to determine the voltage across a capacitor when the current given is 6 e raised to power 6 into exponential minus 3000 t milliampere. The value of the capacitance of the capacitor is 2 microfarad, and we have to consider that the initial voltage stored voltage of the capacitor is 0. So what will be the voltage at this current level? So by formula, you know that the voltage across the capacitor is given as 1 by C integral or antiderivative of I dt plus V of 0, as we are given that the initial condition voltage at time t0 is 0. So by inserting in the value, the capacitance value over here and the current value from this equation over here, we get to know that by simple mathematics and using antiderivative of exponential function, which is the exponential function itself with the limits, into 1 over whatever the power is. The power is minus 3000, so it will be 1 over minus 3000 into 10 raised to the power minus 3, because the current was milliampere. So that's why this 10 raised to the power minus 3 appears over here. Now by simple mathematics, applying multiplying all these constants, we get to know that the value over here is this, and applying 0 to t limit on this exponential function, we get to know that this is minus 3000 t into e raised to power minus 3000 into 0. Anything powered 0 is 1. So this equation simplifies to the final voltage across the capacitor is 1 minus e raised to power minus 3000 t volts. Now we have a practice problem followed by this example, which is more or less similar to this example. I'm going to solve this for you. In this case, we are given a capacitor value of 100 microfarad and the current value is given. We have to find the voltage across this capacitor at two different time levels, at t is equal to 1 millisecond and at t is equal to 5 millisecond. We have to take the initial condition voltage at time t0 is 0. So as we use the formula for voltage in the previous example, it's the same formula over here. V of 0 is 0, so I'll insert plus 0 over here, which we do not need to show. By inserting it the value 100 microfarad and the current equation which was given in the question, and simply removing the constants from the antiderivative and taking the antiderivative of sine, which is minus cos of the angle, and then integral of the angle should be also there. If it's not there, then we'll multiply it by the 1 into denominator of this angle, which is 120 pi. Everything other than t will appear here. Now by simply putting in the limits of antiderivative, we get to know that this all simplifies to this value. V is equal to 1.326 1 minus cos. Every single step has been done for you. In case you still have any confusions, please do let me know. It is very simple. Now we had two conditions, two time limits at which we had to find the value of the voltage. The first is t is equal to 1 millisecond. So in this equation we put the value of t, which is in the trigonometric function cos, so 120 pi into 1 millisecond. By simple using calculator, you can simply find first of all the product of this function and then the cos of this entire angle, and by inserting it values, we get to know that the voltage at time t is equal to 1 millisecond is 93.14 millivolt. Now in the second part, we had to find the voltage at time t is equal to 5 millisecond. Now I'll put, instead of t, 5 millisecond over here, and by calculations using calculator, you can first simplify this product and then take the cos of this angle, and simply doing the simple basic mathematics, we get to know that at t is equal to 5 millisecond, the voltage across the capacitor is 1.62 volts. Now moving on, we have to find the energy stored in the capacitor under DC conditions, which is given. A similar scenario is given in example 6.5. Here we have a circuit. In this circuit we have two capacitors, one over here and one over here. These parallel lines indicate the capacitor. This is the sign of the resistor, and this is a current source. Now we have to find the energy stored in each of the capacitor under DC conditions. So under DC conditions, you know that in lecture number 13 I told you that a capacitor does not work in DC conditions and it is open circuit. Now open circuiting both the capacitors wherever they were, and I identify, let's say, this capacitor voltage as V1 and the other capacitor voltage as V2. And first of all, before finding the energy stored, we have to find the value of V1 and V2. So you know that any element in series with an open circuit is nullified. This means that this 5 kilo ohm, no current in this end is 0, so this will also encounter a 0 current, and V of 5 kilo ohm is equal to 0 volts. So that's why the effect of 5 kilo ohm is nullified, and we simply can remove this 5 kilo ohm from the circuit. So we have to find V1 and V2 over here. So this means I have to find the current flowing through this branch, that is the 2 kilo ohm in series with the 4 kilo ohm, since my V1 and V2 are both in this related to these two elements. So by simply applying current divider rule, I can find the value of I2, which is the opposite resistor divided by the net resistance in the circuit into the current applied. So by inserting it value 3 kilo ohm, 2 kilo ohm, 4 kilo ohm, and then the net current entering these two branches is 6 milliampere, I get to know that I2 is equal to 2 milliampere. So V1 was V2 kilo ohm, which is I2 into R2 kilo ohm. By simply putting in the value, I get to know that V1 is equal to 4 volt. Now moving on, V2 is V4 kilo ohm. Inserting it the value, I get to know that V2 is equal to 8 volt. Now energy stored formula is half 1 by 2 C V square. Here we have two capacitors, so C1 V1 square. By inserting it the defined values, I get to know that W1 energy stored in the first capacitor is 16 millijoules. Similarly, energy stored in the second capacitors, by putting in the value, I get to know that it is 128 millijoules. Now moving on with a similar scenario, practice problem number 6.5 also have two capacitors, and we have to find the energy stored across these capacitors. In order to find the energy stored, we first need to find the voltage across each of the capacitor given over here. There's 20 microfarad and 30 microfarad. So as you know that under DC conditions, each of the capacitor becomes open circuit. When I open circuit these two capacitors, this is how the circuit looks like. Now V1, it should be the voltage of V3 kilo ohm plus V6 kilo ohm. It will be the summation of these two voltages, which will give me the total value of V1. However, V2, which is in parallel to V3 kilo ohm, and you know that parallel voltages are same, so V2 is equal to V3 kilo ohm. However, V1 is voltage of 3 kilo ohm plus voltage of 6 kilo ohm. So now we have to find the individual voltages, and then we can find the net voltage. So the above circuit can be simply simplified to a single loop circuit. It is a single loop in which the applied voltage is 50 volt, and I have three resistances in series. So I can find the current in this loop, which is V applied by R total. This is the three total resistance which sum up to 10 kilo ohm. The applied voltage is 50 volt. So I get to know that the current flowing through this series circuit is 5 milliampere. Now any voltage can be found. V3 kilo ohm would be R3 kilo ohm multiplying the current by the resistance value, which is given by Ohm's law. I can find the value of resistance voltage across each of the resistance. So since V1 was 3 kilo ohm plus 6 kilo ohm, 15 plus 30 is 45, and V2 was V3 kilo ohm, which is 15 volts. Now moving on, we have to use the energy formula, which was 1 by 2 CV square. Since we have two capacitors, so we'll indicate C1 V1 as indicators for each of the capacitors. So W1 comes up to 20.25 and W2 is 1 by 2 C2 V2 square. It becomes 1 by 2 30 microfarad, and this is how I get to know that W2 is 3.375 millijoules. So I have performed almost each single step for you in both the examples and the practice problems, and I would now expect you to please try to attempt the exercise problems that are given at the end of chapter number 6 related to this capacitors topic. And the next assignment and quiz will be from capacitors and inductors topic, so please try to attempt these questions. In case you have any problems, please do let me know in the question answer session. Thank you very much. I wish you best of luck. Take care. Allah Hafiz.